So now we're going to expand on the idea of distance, and we're going to start that by considering a particular property. And that's the property that two distinct points lie on exactly one line. So essentially what that says is, we know that for any 2 points I should be able to draw a line between them, but this says that for any 2 points there's only one line between them. However, so far nothing that we've done says that this is valid in general for geometry. Axiom 0 just says that a line needs to be a proper subset, so that doesn't help. The first one, axiom 1, just says that every line has at least 2 members. That doesn't violate anything. And then axiom 2 just says that there exist 2 points and each 2 points belong to some line. So it doesn't say anything about uniqueness of that line. Axiom 3 has to do with distance, which doesn't help me with this at all. So is this possible? Is it ever possible to have 2 lines intersect in 2 different points? And the surprising answer is yes. And in order to see this, I'm going to consider the case of a sphere. So on a sphere, lines are great circles, so kind of like diameter circles. They're the biggest circles that we can possibly get around. Here's one, and here's another. And we can see these actually intersect at 2 points, right here and right here. And so if we want to include spherical geometry in our study, we must somehow allow this behavior where it's possible to get more than one line through 2 points. So our main idea and the key concept that's going to allow for this is the idea of distance. In Euclidean geometry, the geometry that we think of most often, the geometry we learn in high school, distance is unbounded. I can make 2 points as far away as I want them to be. However, for spherical geometry, distance is now bounded. There is a maximum possible distance that 2 points can be. So we can't have the idea that 2 points can be as far away as we want. There is a maximum distance that they can be apart on a sphere. And on a sphere, 2 points that are the maximum possible distance apart have an infinite number of lines between them. So this only works if they're the maximum distance apart. To expand on this more, we're going to define this thing the least upper bound. We're going to start by assuming we have 2 points, x and y. So the maximum distance between these points is the least upper bound for distance. It's the maximum thing they actually can be. So the idea of this, if I know that the maximum 2 points can be away is 10, 10 would be the least upper bound. 200 is still a bound for this distance, but it's not the smallest. So that's the idea of the least upper bound. It is the maximum possible distance they can be away. And we're going to denote this by the Greek letter alpha. So let's look at a couple of properties about this least upper bound. The first, for any 2 points, we have to have that the distance between them is less than or equal to alpha. It can't be bigger than, it has to be less than or equal. We're going to say that alpha is less than infinity means that alpha is an actual real number, like 20 or something like that. In Euclidean geometry, where this is unbounded, then we just say alpha is equal to infinity. So alpha equal to infinity means there is no maximum distance. Alpha less than infinity means there is. On a sphere, if my 2 points are less than alpha, my maximum possible distance, then they cannot be poles. So poles are like the endpoints of a diameter of the circle. They can't be polar opposites of each other. On the other hand, if they are actually equal to alpha, then they will be poles. And in this case where the distance is strictly less than alpha, there's only going to be one great circle or line passing through these 2 points. So if their distance is not the maximum distance away, then lines between 2 points will be unique. Now that we have this idea of a bounded distance, we can do our fourth axiom. The first piece of axiom 4 says that if alpha is less than infinity, so the bounded case, and the distance between 2 points is less than alpha, then they lie on exactly one line. So if I know my distance is bounded and I know these 2 points are not the maximum distance, the line between them will be unique. And then the second part of this axiom, if alpha is equal to infinity, so if distance is unbounded, then 2 distinct points determine a unique line. So if I know my distance is unbounded, any 2 points, there will be exactly one line between them. Now that I have this idea, I can actually start to denote lines. So I need to consider 2 points, A and B, with 0 less than AB less than alpha. So it has to be greater than 0, meaning these need to be 2 distinct points. And it has to be less than alpha. They can't be polar opposites on a sphere. Anything else, any other 2 points are fine as long as the line between them is unique. And now I can denote them with the familiar line symbol. AB with a line over the top of it will denote the line between these 2 points. I'm now going to assume that C and D are also on this line, and once again, C and D are not polar opposites, and they are 2 distinct points. In that case, the line AB and the line CD are the same line, so there's nothing unique about the way we write this. So there's nothing unique about the 2 points that we pick for the line. As long as it's any 2 points on the line, we can define it. And the last thing that this tells us, if we have 2 lines, L and M, and we know they intersect at 2 distinct points, A and B, then the distance between A and B is equal to alpha. So they are actually polar opposites. They are the maximum possible distance apart on this sphere. 2 lines will always intersect at these 2 points that are exactly polar opposites of each other.